organizer, for this opportunity. I'm gonna tell you a little bit what is quantum computation about. Okay, you can see here this picture. This picture has nothing to do with quantum computation at all, but if you type in Google quantum computers, you get this picture, okay? But it has nothing to do completely. Okay. So what can a quantum computer do? So we have a traditional computer, the laptop we have, or the supercomputers we have in research centers to perform calculations, and they have limitations in the speed they can calculate things. Okay, there are certain problems that they can solve, not because they are not able to solve the equations, but because it will take too much time. It will take maybe the age of the universe to solve those problems. However, if you have a quantum computer, you could solve those problems in a reasonable amount of time. Okay, so it's like you have a super fast computer. There is an important thing to say. Quantum computers can solve certain problems faster than a normal computer, not all the problems, okay? So in that sense, a quantum computer will not be a substitute of our personal computer. And it's a big topic because NASA, IBM and Google, they have laboratories explicitly dedicated to quantum computation. They are investing millions and millions of dollars on developing this field, so it's something which is really big. Let's start off with, doesn't matter. Let's start how like classical computer work. So we have transistors, with basically a transistor, if you have current passing through a transistor, you have a 1 bit, which is 1. And if there is no current passing, it's 0, which is the bit 0. Then if you combine transistors together, you can make, put many of them together and you make a logic gate. With a logic gate, you can transform those bits. Okay, so here I have, which is called normally in quantum computation, well in standard computation, an AND gate. So we have a set of inputs, A and B. So for instance, if A and B, both of them are 0, the output is 0. 0, 1 is 0, and there is like this a conversion table. And it is just 1 if both of them are 1. So what we can do is, we have certain bits, which are the inputs, and by applying transformation, we can transform them in another bit, in another 0 or in another 1. If we combine many logic gates together, we have an integrated circuit, and this can perform more advanced tasks like sum, multiplication, comparison. Basically, you can also put many of these integrated circuits all together and then make a computer, the computer you know. So basically, this is what classical computation do. They take an input, they transform it in an output, okay? But one by one at a time. Then we can go to the weirdness of quantum physics. We have a weird phenomena, like you probably know, Schrodinger's cat. This event is called superposition. In quantum physics, you can have two particles can be in two states, or one particle can be in several states at the same time. And this is what the Schrodinger cats represent. So probably you know Schrodinger cat is a paradox, like Erwin and Schrodinger developed to try to explain this kind of the concept of superposition. Basically, the way it works is you have a cat in a box, and then there is a mechanism that can randomly trigger a mechanism to kill the cat. So then if you don't open the cat or don't take a look at the box, you don't know if the cat is either dead or alive, so it is in a superposition state. This is an analogy. Of course, this doesn't work in cats. This thing just applies to quantum particles, so really isolated systems, atoms. But in the quantum world, you can have two atoms in the same state. You can also have quantum entanglement, which basically is two particles that interact together. If after that interaction, they don't interact with anything else, they will remember that interaction forever. That means if something happens to one particle, the other particle will be affected immediately, even if they are in the other part of the universe. And that is an interesting effect that you can exploit. Also, you have wave-particle duality. In quantum physics, particles are not really like these tiny balls we tend to imagine, but they are also waves. They are the wave-particle duality. They behave, they can show both behaviors at the same time. All of these phenomena, you can use it to make computation as well. And as you can imagine, this is really weird. So if you use this weird phenomena that we are not used to, you will get also weird results. So then how can we integrate this in quantum computers? So first, the thing we need to introduce is the notion or the concept of quantum bits or qubits. In quantum computing, instead of having bits, we have quantum bits. And to name them, I have introduced them in these little cases, okay? So we can have the state 1 or the state 0, as we had before, like in classical computation. But we also can have the Schrödinger state, that superposition state, which is this combination. We can have combinations of both the states at the same time. And that allows us to perform third-time operations that are not possible in the classical computer. In the same way we had in the classical computation, we can do quantum gates. Okay, so here we have an input A, an input B. So these are the input, here is the quantum gate, and then we have an output. So let's take a look at an example. I have this input here, which is 1, 1 minus 1, 0. If I transform it, I apply a quantum gate to it, it's transformed in 1, 0 and minus 1, 1. So it completely reverses the state. If you realize, this is not a single state. Before, in a classical computer, we have or just 1 or just 0. Here we have a combination of many inputs. The point is, just by doing one operation in this combination, we can transform the whole thing with just one operation. Maybe you're thinking, okay, there is an analogy with parallel computation where you actually compute several quantities at the same time. Okay, in that case, you compute several quantities parallelly, but you have to do the computations. So imagine that you have some process, you have 70 processes, all of them in a parallel, so it takes 1 second to do the 70 of them. At the end if you count, you did 70 processes. In the quantum computation, if you have 70 of these inputs, you can change them all at the same time with just one operation. That is the key of the speeding up in the quantum computers. So you can think, thanks to this quantum weirdness, you can think of operations where you compute many quantities in just one go. And that is the key for the speeding up process in quantum computation. Of course, you put together several quantum gates and then you end up with a quantum processor. Then I'm going to give you some examples of how these quantum computers, of some quantum algorithms, and the relationship with data. So the first one is the source factorization. This is Peter Shor, the guy who invented this algorithm. And basically it's an algorithm to factorize numbers. So you might know 15 is 5 times 3, 21, 7 times 3, and so on and so on. But as soon as the number gets bigger, it takes more time to factorize this. Okay? So here I have this is the Shor factorization algorithm, and this is a comparison between the classical computer, the time it takes as a function of the number of bits you have in your number, and then in red you have the quantum computer. So you can see the difference in time is really big. How can this be applied in our daily life? So it's in encryption, data encryption and data security. Basically, you can imagine your whatever type of data you want to encode, bank data or I don't know, your email data and so on. You have two types of keys. You have the private keys, which are secret keys, which are 2 prime numbers that only you know, and then you have a public key, which is basically the multiplication of those 2 numbers. And this key, you share it with everyone. That everyone encodes the messages using this key, and then you recuperate the message, because you know the keys, the 2 prime numbers, you can decode the message. These numbers typically are, this is an example, they are way bigger. And then this is really hard to, if you want to, let's say, to factorize these numbers, it's impossible with the computer we have now. It would take more than the age of the universe. However, with a quantum computer, you could make it in just minutes. So this algorithm allows you to do that. Wait. Another example is quantum Grover search. So this algorithm is useful to solve the salesman travel problem. So basically, you might know there is this long-standing problem that you have several cities and a salesman has to visit all the cities. Which is the optimal way? So depending on the numbers of cities you have, for instance, you have 6 cities, you have 720 possibilities of 720 different ways you can follow. And to find which is the optimal, you should test them all. So it takes a lot of time. Using global search algorithm, just with 27 attempts, you can find the optimal way. Okay? And this is thanks, again, to the weirdness of this quantum computation. So you can see there are many problems that can be tackled by quantum computer, but what is the reality of quantum computers right now? Well, the record in factor S in a number is 21, so it's not useful. Let's say you can do it faster, probably by hand. Then it's also important the error correction. So every time you compute a quantity in a computer, you have errors, and that error rate must be low. Nowadays, we have the best, let's say, qubits that we have can make one error out of 15,000 calculations, which is still really high compared to classical computers. Then, to exploit all these events, you need to combine all these qubits together. As I said before, you combine them via entanglement. The record in number of qubits entangled is 14, so it's not high. To do things useful, we will need around 50, and just to add more qubit entangled to the whole system is really, really difficult. And for instance, for the last one, the superposition time. This Schrödinger cat state. For how long can you hold this quantum state? So the record is 39 minutes, which is not much. So after that time, you should restart the system and so on. So the reality for quantum computers is there is still a lot of research to be done, a lot of technical improvement. But the proof of concept is there. There have been studies and proofs that all this is feasible. We just need more engineers and more research to have this become a reality. Thanks a lot.